This is the Chem 1 lecture for 14A, Intro to Solutions. So we're starting a new unit today. It is short and sweet. Please have your notes out and be ready to take notes as you watch this ed puzzle. So we talked about the word solutions way back in probably in the fall, Unit 2, and we defined a solution as a homogeneous mixture made up of two substances. So remember, there was homogeneous and heterogeneous. Homogeneous means it looks the same. So like Kool-Aid powder with water mixes and it looks like one solution, versus heterogeneous would be like trail mix. You can still see the different parts. A solution is typically made from a solid and a liquid. And what we're going to dive more into detail with this whole unit is a solution consists of two parts, the solute and the solvent. All right, so first definition for today is the solute. This is the portion of the solution that is being dissolved. An example would be salt or sugar, and it's those little orange particles in this picture. So the thing that is able to be dissolved. The solvent is the part of the solution that is doing the dissolving. And so this is typically exists in a larger amount, and a very common solvent is water. Water is known as the universal solvent. It is so good at dissolving things. So we have two vocab words that can describe a solution and how much solute versus solvent there is. If we call a solution concentrated, we are saying that there is a high amount of solute and a low amount of solvent. This might taste like lemonade that is like really, really tart, like meaning there's a lot more sugar and lemonade in there and there's not as much water. That is very concentrated. You might see the word concentrated on laundry detergents. It's just, you don't need a lot. There is a lot of solute per solvent. Versus dilute, there is a low amount of solute compared to the solvent. So this would be lemonade or Kool-Aid that taste very watery. There's a lot of water, which is a type of solvent, but there's not a lot of solute like sugar. So instead of describing something just as it has a high solute versus a low solvent, we can actually put a quantitative number to how concentrated or dilute solutions are. So the formula we're going to go over today is called percent by mass. And so that will tell us the percent of solute in a solution. And you solve this by taking the grams of solute divided by the grams of solution. And remember, solution is made up of two parts. So to get grams of solution, you add up the solute and the solvent. Notice that our units are all about grams. That's why we're calling it percent by mass. So let's look at example number 1. It says, what is the percent of solute of a solution made by mixing 35 grams of chloride with 85 grams of water? So 35 grams of chloride is the solute. Remember, the solute is what is being dissolved. It's typically in the smaller amount. And then 85 grams of water is the solvent. So for us to calculate percent, we need the grams of solute, 35, over, and this is where we see mistakes every year, over solution, which is a total. And remember, solution is solute plus solvent. So that's going to be 35 plus 85 times 100. So 35 over 120, 35 divided by 120 times 100 gives us our percent as 29.17%. So our solution is 29% solute. And as you've been catching on with anytime we give you a math formula, we don't always have to give you the same variables. As long as we just give you 2 of the 3, you can solve for the missing one. So I want to work through example number 2. And it wants to know how much water is added to 35 grams of glucose in order to make a 5% solution. So if I label things, 35 grams of glucose, that's going to be the solute, and they've given us the percent. we're looking for the solvent of water. And as a tip for this entire unit, anytime the question's asking you about water, it's going to be a two-step process. So step one would be to first solve for the total grams of solution. So I'm going to use our new formula today, percent by mass, percent equals grams of solute over that total grams of solution times 100. And from my example 2, I can plug in the percent. We know our solution is 5% glucose. We know glucose is our solute of 35 grams. And then I'm just going to do X as representing my total. Now, for those of you math whizzes, you could do this in one step if you did 35 plus X, and this X was representing solvent. But you have to be really good at your algebra because you're going to be distributing and stuff like that. So what I recommend is break it down into just 2 steps, and big X is representing the total grams of solution, and then we'll subtract off the solute in our second step. All right, so I've subbed in what I know. I'm going to now try to solve for X, and so I'll first divide each side by 100 and get 0.05 equals 35 over X. Because X is on the bottom, we need to get it to the top. I personally like to make a fraction, so I put it something over 1 because it doesn't change the value, and then I cross multiply and divide. So 35 times 1 is 35, divide by 0.05, that is going to give me the value of X, which is 700 grams. Remember, X stood for grams of solution, but the question wants to know how much water are we adding? So we know a solution is made up of 2 parts, the solute and the solvent. And so if I know my total is 700 and one of the parts is 35 grams, if I subtract those 2, then I will get the other part, which in this case is water or the solvent. So the answer would be 665 grams of water. That's how much would be added in order to make these proportions work. Let's talk about factors affecting how much solute you can dissolve into your solution. And so the first question is going to be, what state of matter is your solute? If your solute is a solid, it's going to have different factors than if your solute is, let's say, in a gas phase. So let's talk about a solid solute and the factors that affect its ability to dissolve. And let's just think of the example of sugar water. So if I want to dissolve more sugar in my water, what factors would I change? One of them is going to be temperature. If I increase the temperature, I can dissolve more solid solute. Think about if I'm trying to dissolve sugar in water, the hotter the water, the more sugar I can dissolve. The other thing is if I drop a sugar cube in, I'm probably going to want to immediately stir it, or we call that agitation. So when I'm stirring it around or increasing agitation, I'm increasing solubility. And that's due to this idea that is solute-solvent contact. So the more I can get the solute to touch the solvent, I'm going to be able to dissolve it more. So we're increasing the solute-solvent contact. The one factor that would not impact my solid dissolving in a solution is if I increase or decrease pressure. So because solids have a defined volume, there is no effect on solubility by changing the pressure. Now, one other factor we did not talk about would also be something called surface area. So if I were to crush up my sugar cube, I would also increase the solubility. All right, so these are ways to increase the solubility of a solid solute. Now let's talk about if our solution has a gas solute. So for example, a soda, the solute is your carbon dioxide, your CO2. So if I want to increase my solute that's a gas, I don't want to heat my soda up. That's not going to keep a gas in. I'm going to want to decrease the temperature in order to increase the gas solubility. And the reason why is gases are active and moving, and so we want to lower their energy so that they're not going to escape out of our solution, out of our soda can. So keeping it at a low temperature will slow down those gas molecules. Pressure will have an impact on gases because they do have that indefinite volume. So if I increase the pressure of a solution, I can dissolve more gas into the solution. So I would increase solubility of a gas. And that's why when you open a soda, you hear that ksh, because it's been bottled under high pressure in order to dissolve as much gas as possible. And then the last factor would be agitation. So you would want to decrease agitation if you're wanting to increase the amount of solute of a gas dissolved in your solution, because you don't want high movement. You don't want to give the gas more movement. We're trying to keep it slow and inside our solution. So word to the wise, when you're answering a multiple choice question and they're asking you about solubility, you really need to pay attention to the detail of, is the solute a solid or is it a gas? All right, our final thing for today's lesson is something called colligative properties. And that is the idea that when you add a solute to a solution, you are going to change the physical properties of that solvent. So for example, pure water is going to boil at 100 degrees Celsius and it is going to freeze at 0 degrees Celsius. However, when you add in a solute, whether it be sugar, salt, anything, it is going to change the boiling point and the freezing point. So let's look at what's going to happen. So if we're talking about boiling point, typically, like when we're trying to boil something, we're having to break the intermolecular forces in the molecules. When you add a solute, you are increasing the intermolecular forces. So it's going to take even more energy to boil a solution, right? Something that has a solute and a solvent in it. So now, instead of water boiling at about 100 degrees, if you dump in a ton of salt, it might boil at 105. So it's having to put in more energy to break more intermolecular forces. And so some people utilize this when they put salt in water when they're boiling pasta, that is making the temperature hotter, right? So now when the salt water is boiling, it's now maybe 105 degrees. And with the temperature hotter, the food could cook faster. Colligative properties is completely dependent on how much of the solute you put in. So if you just put a sprinkle of salt into your pasta water, it's probably still going to boil at 100 degrees Celsius. I think the real reason people do that is just it creates a saline solution so that the pasta noodles don't stick together. But what I want you to know is that the boiling point would increase of a solution compared to its pure kind of solvent. I can't put an exact number to it, but let's just guess. And now it's going to maybe boil at 105 degrees Celsius. Well, let's talk about the opposite effect. What happens if we put a solute into water and we are wanting to freeze it? So in order for something to freeze, they form orderly patterns. But when you add a solute in, it disrupts the formation of the crystals. So it's not going to freeze at its normal temperature. You're going to have to take out even more energy. You're going to have to drop or lower the freezing point in order to get that pattern or that crystal formation to happen again. And so the freezing point, instead of water freezing at 0, now maybe it's if you add in, let's say, salt to water, let's say now it maybe will not become a solid until maybe -5 degrees. Remember, it's dependent on how much you add. So this happens when you make homemade ice cream. You've got to have rock salt you put on the ice. Well, by doing that, you're going to drop the temperature. And then that will allow your ice cream to freeze. So if you notice, whether it's a boiling point or freezing point, like both numbers have gone in the opposite direction. So if we're using the example of water, water is going to stay a liquid longer when you add a solute into it.